I'm going to talk about, well, this is just a generic name, tracing the signal and heterodyne techniques and radio astronomy, and in particular the IF systems, that's the intermediate frequencies. But before I get into the electronics, whoops, I guess I might as well do it in slideshow mode here. There we go. I'll just go over quickly the optics of the telescope. It's an off-axis design. So light, of course, bounces off the big primary, and it can bounce off a secondary, which is quite big. It's 8 meters. You see a person up here on the secondary here. And so the light goes off the primary, hits the secondary, and goes down into what we call the receiver cabin. And these are all the cabins, the receivers. And the receivers rotate around on the telescope. So you can pick the different receivers, you put them in focus, and this is looking underneath the top of the platform where the feed horns are, down below, and this is where the receiver is inside the receiver room. And if you ever make it to Green Bank, you would get a tour and see that. And I'd be remiss not to mention that we do have an active surface, and this enables our telescope to observe all the way up to 3 millimeters by changing and maintaining an accurate paraboloid as you tip this 100-meter telescope over. So heterodyne, what does that actually mean? Radio astronomy is different than almost all the other fields of astronomy in the sense that we treat the electromagnetic radiation as a wave. We're using the wave properties of the light. We care about both the amplitude and the phase. Most other astronomical methods treat the incoming radiation more as photons. You just have photons slapping into the CCD or heating up a piece of equipment like with bolometers. But we on radio astronomy are using the phase information, and we take advantage of that since we know the phase of the radiation. Well, we can mix in something that we know very accurately with what we call a local oscillator. That's where you see the LO. And if you see astronomy block diagrams, those are the X's, the little X. Let me get my cursor here. So that's a block diagram. So you mix in something that you know with an input signal, and you get a new output signal. But since you know exactly what you put in, you can actually infer what the input signal is. And we do this because it's a lot cheaper to have you can look at a lot of different frequencies on the sky using the same electronics. You wouldn't necessarily need. And also the electronics are cheaper if they're at lower frequency. Looking at the case at very high frequency, a lot of electronic equipment is very expensive, and it doesn't exist actually. High frequency amplifiers are very challenging to make. So you'd want to basically, what we say, mix it down to lower frequency so you can deal with it easier. So that's what we do in radio astronomy. The stages in terms of the way to look at it. You use the antenna, of course, is a big light bucket. It collects the radiation. I can't even see my whole slide. I see pictures. I'm gonna kill something off here. That is, shoot. Okay, now I can see my slides. And then we have what we call the front end, the receiver. That includes the feed horn and the low, we call it a low noise amplifier. If you ever see LNA, that's what that stands for. That amplifies the signal. The LO is mixed in at that phase. And then we transmit that, what we call IF, the intermediate frequency, to the back end, which is used to digitize the signal and actually make the measurements. So if you look at it schematically, it looks like that, where you have the receiver, that front end, that's the cold part of the receiver. And then the front end includes some electronics. Then it ships out an intermediate frequency, and then you have the IF frequencies, and then it goes, and that's on the GBTs, that's up in the receiver cabin. We have part of it in the receiver cabin. Then we have a 2-kilometer optical fiber that goes down into the Jansky lab. and then it eventually makes it to our back end. So that's a very crude way of looking at it. If you look at a specific block diagram here, this is for L-band. It shows an example case. We don't need to go into that, but usually when we show block diagrams, we simplify it. We just show, one of the stages, but the frequencies are getting changed a lot with the GBT system in terms of we have a lot of electronics, and that enables us with different switches and stuff to be able to, it's very flexible in how we can configure pieces of equipment. But anyway, there's the receiver. The IF system, really, if you look at it, like the bulk of the block diagram is taken up with the IF system. And there's a local oscillator, and there's your back end. Okay, I already said this, but the main point, the reason we do this, it allows the connection of a lot of different receivers covering a wide range of different frequencies to the same back end hardware. And this is just a chart from the GBT proposal guide showing all the different receivers we have covering a range of frequency from 300 megahertz all the way up to 3 millimeters, 110 gigahertz. So here's a picture of different symbols. This isn't going to be part of the quiz, but fires are little triangles, and mixers, as I said, are X's, and then you can have attenuators and multipliers and splitters and filters and switches, and anyway, you won't have to learn how to read a block diagram, but some of the information is useful for future reference. When I say filters, we have different types of filters. We can have a bandpass filter, basically that blocks all the emission outside that range of frequency of interest. Say you care about observing something here and you want to block everything else out. This is very useful for RFI purposes. Like if you have a very noisy radio environment, you'd want to block everything else out except the narrow region in which you care about. We use a lot of low pass and high pass filters. Basically, it's a way to filter out frequencies. Low pass means you let all the low frequency in and you get rid of all the high frequency, and the high pass is the reverse. The notch filter is the inverse of the bandpass filter. This is a case, let's say you have airport radar in which we have a notch filter in at L-band that's right here. You know exactly where it is, so you just put a notch filter in so you don't see you try to minimize the effects of that RFI. Okay, the types of mixers. We have, the way you look at it, you're mixing it in, it's mixed in. You have waves mixing in as combinations of sines and cosines. In principle, you can actually have multiplication factors of integers that can be more than one, but typically we just use, they're typically just 1 or -1. And we have this different types of terminology, such as up conversion, which means that your intermediate frequency is higher than your observed frequency. Down conversion means the reverse. But when you do observe and when you do mix in the signal, you actually can see, you get both sidebands, an upper sideband and the lower sideband. The GBT, we generally reject the sideband that we don't care about. It's effectively filtered away. So we do single sideband observations. A lot of millimeter telescopes, especially, they use the SIS mixers where they actually mix before they amplify. And a lot of those are dual sidebands, meaning you get both the upper and lower sideband within your IF. Look at it schematically across the frequency. Here it shows an example where you have an LO here. Your sky signal, you have a lower sideband and an upper sideband, and the intermediate frequency is the difference between your sidebands and your LO. So your IF frequencies here. So this is a case where you're down converting, basically. You're observing way up here in frequency. You mix it in with a high LO frequency. The difference between the LO pair is the IF frequency, and you get the upper and the lower sideband. So what you get out is a combination of both, the upper and lower sideband. And I'm not going to go through all the math. I made this for a summer school that was a sort of a different level. but we have different ways to do the sideband rejection. As I said, the GBT usually filters it out, a single sideband. So you basically put in a filter, so you won't, or at least the receiver itself can be a filter. So your sideband is outside the receiver's range of sensitivity. There are other techniques, an IQ mixing scheme. We do this on the Argus instrument. It actually uses an IQ mixing scheme at 3 millimeters because the LO frequency is within the bandwidth from which we're observing. Well, I have this picture. This shows a picture of the receiver room. And I'm just going to go through some slides. Now, these are technical pictures that show you're pulling up our tools in which to look at things with the GBT, and I just show it because there are a lot of different options. This is our LO oscillator, and we have a bunch of different switches in which we can connect different things. Software does all these connections for us because you can be quite complex to connect all the switches required to get the signal down through all the different pieces of electronics. So this LO, besides switching down to a different IF frequency, we use it to correct for Doppler tracking. So the Earth is moving around the sun, the Earth is rotating, and anyway, you can correct, we know how everything's moving, so we can actually correct for the velocity frame, so we can keep the source of interest in velocity space where we want it in the center of the band as a function of time. And there's different reference frames that one can choose. So you could, with respect to the sun or with respect to the local standard of rest, LSR. Topocentric means the Earth. And you can choose different types of velocity frames. And then we'll already mention for frequency switching, you use the LO. You can switch quickly with frequency switching. Won't go through that. We have these are just pictures that show different chunks of the GBT system. Here's the actual pictures. I showed you some pictures earlier, the receivers on the telescope. This is the equipment room. It's nothing exciting. It's just pictures of computer racks, basically, and more electronics. Graphically, I show this picture. We can use this in one of the exercises. The converter rack. So once the signal comes in off the optical fiber, change in, and we have a whole other IF system within the equipment room, getting it ready for the back end, which is what typically most people use Vegas now. So you have all these electronics equipments, and a key point is the idea is you want to keep everything in the linear regime, meaning if you give it an input power, if you double it, you measure something that's double. That way you can calibrate it. So when you set up a system, you need the system, what we have this routine called balance, and it will set all the levels. So all the electronics are balanced up and leveled in a way so they'll all work together and maintain the optimal power levels. So now we're going to get into a little bit of an example. So I want to walk you through the example for the GBT for Argus, which is our highest frequency receiver on the GBT. Some ways it's most complicated, in other ways it's the simplest. This is the block diagram. And here I said you wouldn't have to understand this, and here I'm going to go through it all. We observe at 3 millimeters, the sky frequency here. We're going to do this case where we're going to try to observe HCN and HCO plus, which are they're roughly about 90 gigahertz, and we're going to put it in the lower sideband. So our sky frequency, we'll pick 89 gigahertz to get both of them in between those two lines. We're going to put that in the lower sideband. That's what's coming into the feed horn, and that's going to be in the lower sideband, but also we're sensitive to this thing in the upper sideband, the image sideband, which is the IF frequency times 2 away. So the LO is mixed in. I won't go through all these parts. There's 16 channels, so it's copied. We have one LO, and it gets copied into 16 different outputs to go to all the different receiver blocks. The LO is at 90.525. When that's mixed in with the sky frequency, you get an output frequency of the IF in the lower sideband of 1.525. That's just 90.525 minus 89. And that's the frequency that goes down the optical fibers and heads its way towards the receiver room. Not the receiver room, excuse me, the equipment room. So in the equipment room, it comes in at 1.525 gigahertz. We mix it again with an LO at 11.275, and it spits out a new IF frequency, which I call IF2, which is at 9.75 gigahertz. And that's in between. This shows this diagram, this little block here shows that's a little filter that lets in frequency range over that bandpass from 8.5 to 10.35. We're not done yet. We mix it again with 10.5 gigahertz, and that brings it down to 0.75 gigahertz, and that's why that's the actual IF3 frequency that actually goes to the spectrometer, which is our Vegas. Why do we do all these mixings? In this particular case, it's sort of silly. You wouldn't have to necessarily do that, but other frequencies and bandwidths, there's advantages of doing, we do this double mixing where you mix it up and then you mix it down, and then basically you basically can throw away the frequencies either on the high side of your targeted bandpass or your low side. So that's the technique we use to even if we were mixing, if the receiver itself didn't filter out the image sideband, this double mixing technique would. Okay, so I'm not sure of the time, but here we'll do a simpler case here with L-band. So this is going to be your quiz, so to speak, and basically have 3 questions to answer, but let me set it up here. An observer wants to use the L-band receiver, so that's the low frequency receiver on the telescope, to measure H1, 1420, which we've been talking about that all day, and we want to use the narrowest possible bandwidth with the Vegas spectrometer. And the reason we picked the lowest bandwidth is to minimize the RFI. So we don't have the output bandwidth is 11.72 megahertz. The exact bandwidth you don't need to care about, but it's around 12 megahertz. Okay, so for an input frequency of 1420 megahertz, and now these are the questions. What is a required LO1 frequency? What is the center IF frequency? And pick the appropriate choice of filters for the observations based on the block diagram before. So we have 3 questions. So 1, you want to pick a filter here. You need to pick another filter here. And they want to know what, and the question is, I guess there's 4 questions because you have 2 filter questions, and then we have which IF frequency that you can use, and what LO do you need. And one key piece of information that's specific to the GBT is these options here, at least from our receivers, you either center the frequencies around 3 gigahertz or 6 gigahertz, because all of our filters from the IF rack are centered around 3 gigahertz and 6 gigahertz. So this is, you don't really have to compute this, you just have to pick one of these 2. And then you pick one of these filters here, and by picking this over here, you basically can work backwards and compute what that LO1 frequency is. So I am going to stop my share so I can see what kind of questions are there. And you guys have, I'll give you whatever, of order 10 minutes to think about this. And while I'll take questions. So let's see if I can stop share. There's probably lots of questions.
Not too many questions yet. We had one a little bit earlier in the talk, but I didn't want to interrupt you, so maybe we can return to that one at the end. And then we had one question about the frequency of hydrogen emission, and megahertz versus gigahertz, and I answered that. So, but if people do have questions about the quiz portion that Dave just gave you guys, then
Open.
go ahead.
Oh, I'm sorry.
And
That's right. See, this is a good question.
yeah, there's information that you need. So Dave, I'll go ahead and let you know what
Okay.
kind of questions there might be, and you can
All right.
share your screen so that people can see the various different options that they have to choose from.
Now
here.
I hope it's back up. I apologize. When we do this, what we do is we actually obviously hand out sheets of pieces of paper and have people work together in little groups.
Yeah. So if people do have questions, put them in the chat window, and I will also scan the participant list, and you can raise your hand if you are more comfortable speaking as opposed to typing.
And I went through that maybe a little too fast, but I apologize.
That just means there will be more time for questions at the end.
Which is fine. Just for clarity, I didn't actually explicitly say that. This BPF stands for bandpass filter 1, and that's bandpass filter 1 options. So right here, we're picking one of these. And the same thing over here, bandpass filter 2, and here are the bandpass filter 2 options on the GBT. And there's lots of options to pick from there. These little numbers here, these are the amplifiers. This gives you the range on which the amplifiers work over. So here we're observing 1420, which this amplifier works because 1420 is in between the 1150 and 1750. Now, after it gets mixed, there's going to be some other frequency that comes out, not the 1420. And you see this amplifier works from 2700 megahertz to 3400 megahertz. So that gives you a clue on what could come out after that amplifier.